When the night has come and the land is dark and the moon is the only light we'll see. No, I won't be afraid. Oh, I won't be afraid. Just as long as you stand by me. So darling,
Before we begin fabricating our turbine blade, safety always comes first. In the workshop, we prepare ourselves with the right personal protective equipment, including safety goggles, gloves, safety jacket, and safety shoes. During cutting with the hacksaw, we secure the material tightly in a bent vise and cut slowly and steadily to avoid slipping or injury. For drilling, we wear goggles to protect our eyes from metal chips and use a center punch to guide the drill accurately and safely. When milling, we avoid touching the mat workpiece while the cutter is running and maintain a safe distance from the rotating tools. During turning on the blade machine, we make sure the workpiece is securely fixed and the tool is properly set. We avoid wearing gloves, loose clothing, or accessories to prevent them from getting caught. We stand slightly to the side and never touch the rotating part. In the welding process, we use welding glove and welding helmet and make sure the area is well ventilated to avoid harmful fumes. Lastly, during grinding, we wear gloves and hold the part firmly to stay in control and to prevent slipping. With all these safety steps in place, we are ready to begin the fabrication process with confidence and care. We begin by cutting the raw master material using a hacksaw. The metal is held firmly in a bent vise to ensure a straight and accurate cut following the dimension given in the drawing. After cutting, we mark all the hole position clearly using a scribble and ruler. Then, a center punch is used to make a small dent at each mark. This helps the drill bit steady and prevent it from slipping. We proceed to drilling using a pillar drill. A center hole is drilled with a radius R8 along with additional hole of 3mm and 4mm diameter depending on the component requirement. Accurate drilling is important for smooth assembly later. Next, we use a milling machine to cut a slot on the surface. Each piece is milled to a depth of 3mm and in one of the components, the slot is milled all the way through. We make sure the workpiece is clamped tightly and for safety and accuracy. We move on to the lathe machine to shape the outer surface. The material is turned to a radius of 27.5mm to achieve a clean and precise circular profile. Proper speed and tool positioning are used to get a smooth finish. Then, we use a hand tap to create an infiltrate in the required hole. A countersink tool is used to prepare another hole so that the screw head can sit flush with the surface. After all, machining is done. We align the component properly and begins the assembly. Once everything fits correctly, we use spot welding to join them permanently. The welding is done carefully to ensure strength and alignment. Finally, we use a grinder to remove excess weld bits and smooth the surface. This step gives the turbine blade a clean appearance and ensure there are no sharp edges. By following each step carefully, we have successfully fabricated our turbine blade. Throughout the process, we applied workshop skills like cutting, drilling, milling, turning, welding, and grinding, and gained valuable hands-on experience in precision manufacturing. Throughout the fabrication process of our turbine blade, we encountered several challenges, but we managed to overcome them with teamwork and problem solving. The first problem was uneven cutting with the hacksaw. Our initial cut was slightly slanted, which affected the size and shape. To fix this, we clamped the material more securely and followed by the marked line more carefully with a steady sewing motion. The second problem happened during drilling. The drill bit slipped off the mark, causing an off-center hole. To solve this, we used a center punch before drilling to create a small guide point, and we started drilling at a lower speed to stay on track. The third problem occurred while milling the slot. The slot was not perfectly aligned. We double-checked our measurement, tightened the clamping, and slowed down the feed rate to achieve a cleaner and more accurate cut. The fourth problem was thread tapping difficulty. While tapping the M4 thread, the tap tool jammed and caused slight damage to the hole. We overcome this by applying cutting oil, tapping slowly and carefully, and clearing metal chip regularly to avoid tool breakage. The fifth problem happened during grinding. We accidentally removed too much material, which affected the shape and surface finish. To prevent this, we marked the grinding limit clearly and used lighter pressure while grinding to stay in control. This challenge helped us improve our technique and gave us a deeper understanding of precision and teamwork in fabrication. After completing this project, we reflected on the overall process and identified a few improvements that can be made to achieve better results in the future. Firstly, we suggest using jigs or custom clamping tool during drilling and milling. This would help maintain better alignment and reduce error causes by manual setup. Secondly, more practice with threading tools like the hand tap would help avoid jamming or breaking. Having extra test pieces to practice on before working on the actual part could make the process smoother and safer. Lastly, we believe the overall efficiency of the project could be improved by planning our time better. Creating a clear work schedule and assigning specific tasks to each group member would reduce delays and improve teamwork. This improvement would not only enhance the quality of the final product, but also help us more effectively in future workshop projects.